Hello, my name is Menzata Akmal binti Mahat and my student ID is 200000334.
My name is Nurul Anis Matina Aslan and my ID number is 20335.
Hello guys, my name is Alexter bin Anad Rejali with student ID 2000348.
My name is Muhammad Saleh bin Ahmad Idris. My ID number is 200000597.
So now we're going to present an integrated design project on the production of ethylene oxide. For the introduction, you have three divided parts. For introduction, for reaction engineering 1, process modeling simulation, and separation process 2. For reaction engineering 1, the main thing is you want to propose an optimum reaction system for the production of ethylene oxide with the optimal operating condition considering economical and technical feasibility. For process modeling simulation, you want to construct a complete mathematical model that accurately represents the reaction and also to run a simulation to get a clearer picture of the process. And then for separation process 2, we need to describe the separation process system that was applied in the proposed ethylene oxide production plan, and also need to explain the separation technologies that are being used and to discuss the contributions of separation technologies towards the purification of EO. For the production capacity, we need to fulfill 25% of annual demand, so we obtained 7.6 times 10 to the power of 9 kilogram ethylene oxide, which is the minimum amount produced based on the 25% of annual demand. For the proposed location of the plant, we proposed the location to be at Tanjung Lansat, Johor, because it is right next to the naphtha cracker where it supplies the source of ethylene, so it saves money and distance. For the reactor and catalyst, the reactor that we chose is vertical plug flow shell and tube reactors because it is suitable for high velocities and require less volumes. For the catalyst, we chose silver or alumina catalyst because it drives the selectivity of EO until 81%. And these are the properties that are obtained for the catalyst. For the volume is 9.97 meter cube, diameter is 0.008 meter, length is 11.58 meter, and the solid density is 780.1 kilogram per meter cube. For the working of proposed reactor separator system, we chose plug flow reactors because it has higher process stream velocities and require less volume than CSTR. And in plug flow reactors, these are the two reactions that consist. So for partial oxidation, we have oxygen reacted with ethylene to produce EO, and then EO reacted with oxygen for complete oxidation to produce carbon dioxide and water, which are our undesired products. And the yield of ethylene oxide can be high as 95.24%. For the type of reaction involved, we use oxidation with oxygen because it is easier to transport than other chemicals, and water is chosen as the cooling medium because oxidation is highly exothermic process, and this is very important, and also to prevent runaway reactions and the production of hot spots in the reactor, and it also can generate low pressure steam. For the kinetics data, we modeled it using Arrhenius kinetics, and the pre-exponential factors are determined by using iterative method. And for ethylene oxide formation, the activation energy that we obtained is 88.39 kJ per mole, and the pre-exponential factor is 1.1 times 10 to the power of 12 per hour. For ethylene combustion, the activation energy is 120.95 kJ per mole, and the pre-exponential factor is 4.8 times 10 to the power of 14 per hour. And it keeps the selectivity and conversion within the range of 80% and above. Next, for the optimum reaction system for the production of EO, these are the diagram that we sketched. So for the feeds, we have two feeds, which is ethylene and oxygen feed, going through the mixer and then through the PFR, which has the catalyst of silver or alumina, and then the outlet stream, which is the product that we want, and also containing heat exchanger, centrifugal pump, two compressors, and absorption system. For the strategy to maximize the selectivity and yield of EO, first of all, we need to select an appropriate catalyst. In this case, it's silver or alumina, and the selection of optimum reactor is also needed, which is pure plug flow reactor, and also a suitable feed ratio need to be adjusted appropriately, and we need to consistently regenerate and replace the used catalyst. For the reactor sizing, the total volume that we obtained is 8.441 times 10 to the power of negative 9 dm cube. The length is 7.024 times 10 to the power of negative 9, and diameter is 3.912 times 10 to the power of negative 2, and number of tubes is only 1, and wall thickness is 5 times 10 to the power of negative 3 meter. And here are the few assumptions, which are the steady state operation, perfect mixing, and also it is in isothermal condition. For the optimal operating condition, considering economical and technical feasibility, these are the calculations that we have made and obtained that the net profit is 4.27 million, and it is confirmed that our reactor is feasible and economical.
For process modeling and simulation, this is the mathematical model that we developed where A is ethylene, B is oxygen, C is ethylene oxide, and I is inert. So a few assumptions is made, which is the reactor is well insulated, so head loss is negligible. The coolant in rapid flow rate of the coolant stream, so average water coolant temperature is used in the mathematical model. The saturated steam is supplied and condensed. The reactor contents are perfectly mixed and do not exhibit significant gradient. The overall heat transfer coefficient assumed constant. There is negligible vapor pressure and constant heat capacity at operation temperature. As you can see, this is the mass balance for overall mass balance, component mass balance, and also the initial conditions with parameters. For the simulation, this is what we get from the Aspen HYSYS. We use the fluid package and RTL, where the components is ethylene, oxygen, ethylene oxide, carbon dioxide, and water. We use the kinetic reaction, and where the inlet conditions has 24.97 atm pressure, 260 degrees Celsius temperature, and initial flow rate of ethylene is 4.292 kmol per hour, and initial flow rate of oxygen 7.525 kmol per hour, where we use the PFR reactor. So for the validation, an investigation is being conducted into the molar flow rate of ethylene oxide that is produced by the reactor, where we compare the flow rate of ethylene oxide from the manual calculation and from the Aspen HYSYS. So we compare the value. And we use the trial and error method. From what we get, the deviation error is 78.61%, which is higher. So there might be some slight errors where we mentioned in our report. And lastly, for model analysis, for the pressure, where we do the case study, a lower pressure will allow this reactor to operate at higher efficiency. This is due to the conversion rate is going to go up whenever the pressure of the input goes down. So for the temperature, there will be temperature that is optimal. So when we increase or decrease from the optimum temperature, it will result in reduction of the amount of ethylene oxide converted due to the kinetic reaction. Lastly, for the flow rate, an increase in mass flow rate will lead to a greater percentage of conversion. So increase in the likelihood that the reactants will collide with one another and react.
Okay, so let's proceed with the design of the exhaustion column. For the first one is the safety in handling exhaustion column. For the safety in handling the exhaustion tower, there are several measures that are important in order to ensure the safety of handler and longevity of the tower. These failure modes are located and important for person to handle the tower. Design considerations are crucial for providing a safety factor in design. Furthermore, for wrong or defective equipment, there are some measures to prevent, mitigate, and control the failure mode. Next, the selection of adsorption column. Adsorption is a process where solids are used in order to remove a soluble substance from water or any solution. Thus, activated carbon plays an important role in this process. Activated carbon were used in various processes such as waste gas treatment, solvent recovery, and air purification. In this case, we use granular activated carbon as it is efficient in handling gas because it has large surface area for eliminating water and gas. There's a chemical equation that occurs oxidation, which are partial and complete oxidation. Next, we proceed with cost of an adsorption column. A proper adsorption tower must have the following features in order for it to be in a proper condition. First is allowance for integration with other parts of the other machines in different industrial applications. Second, low cost of maintenance. Third, made up of very cheap building material. Fourth, proper cleaning function. And fifth, sensitive to any type of contamination. There are 3 tests that must be performed, which is factory test, installation qualification test, and operational qualification test. To summarize the separation process, we can observe that adsorption tower and member selection unit is important for the project. When it comes to choosing an adsorption tower, many criteria are counted, such as type of adsorption tower, its operational efficiency and safety in handling the tower, and its cost. As for membrane selection unit, it is suitable with sealing and suction diffusion mechanism unit. As for its safety, we need to monitor from time to time the operating temperature of the membrane unit for both adsorption column and membrane selection unit. Moreover, we need to run a regular check on the unit to avoid any safety and efficiency issues.
In conclusion, we as the group members of this integrated design project have worked our best to come out with a reasonable production plan design to produce ethylene oxide. For example, in reaction engineering 1, we have decided to use PFR, or also known as plug flow reactor, to produce the ethylene oxide required in our case study. In this reactor, ethylene will react with oxygen to produce the ethylene oxide. To simulate the operation of this reactor, in process modeling and simulation, we have used one of the simulation software, which is Aspen HYSYS, to make sure that this operation and reactor will work well, will operate well. Last but not least, we have known that the reaction of production of ethylene oxide will produce carbon dioxide and water as the undesired product. Therefore, we require separation technologies to separate these two impurities from the ethylene oxide stream. Therefore, in separation process 2, we will use adsorption column and the silicon rubber membrane unit to separate the carbon dioxide and water from the ethylene oxide. In the adsorption column, the activated carbon, which works as the absorbate, will absorb water vapor and carbon dioxide. However, this will not work at 100% efficiency. Therefore, we add silicon rubber membrane unit to keep separating the carbon dioxide from the ethylene oxide stream. After passing through the membrane unit, the pure ethylene oxide will be transferred to its respective consumers. This is all from our team. Thank you for listening.